Okay, so let's move to the now question number two from the May 2025 paper 2 time zone 2. Okay, so this question is about the thermal energy transfer, and the first question is about the mechanism of heat transfer by conduction, right? So as you know, there are three modes of transfer of heat thermal energy. The one is conduction, the other two are convection and radiation, right? So in conduction, the heat energy, the thermal energy is transferred due to the physical interaction of the one molecule of the one particle to the other particle, okay? Or it is transferred due to the physical interaction between the one object, one body to the other body, okay? So uh, to explain you this thing, I have shown you this diagram where you can see that this part of this rod have relatively these particles have relatively higher energy because we are delivering heat to this part. Now how this heat thermal energy is transferred across the rod, this is across the rod because it possesses more kinetic energy, right? So I can say average kinetic energy, and you know that the temperature is actually the measure of average kinetic energy of the particles microscopically. So this kinetic energy is transferred from these particles to the neighboring particles which are relatively colder, which have a less temperature. So it means that this is transferred due to collision to neighboring particles. So this is a side where the temperature is high, and this is a side where the temperature is low because that possesses the less kinetic energy. So this is the natural flow of the direction of heat, that it always goes from the higher temperature side to the lower temperature side. So due to the collision of the particle, specifically in the conduction method. Okay. So students, this is the mark scheme, and you can see what we have discussed, those main parts that the particles kinetic energy is transferred due to the collision to the adjacent particle atoms, right? These are the key terms that we also discussed. Okay, now let's move to the next question. Okay, as you see that this is a wall. Okay, this wall have this thickness 0.25 meter, and it has the surface area 18 meter square, and inside the temperature is high, right? Whereas the outside the temperature is low, right? So temperature is low, so you can imagine what should be the direction of flow of heat. So the heat will flow from the inside to the outside, but through which mode of transfer of heat? That is conduction. Okay, because the heat is not radiating. Okay, it's not going in a vacuum. Okay, it is not carried by the air, right? So it is carried by the particles of this wall. Okay, so they are transferring the heat, but this thickness matters a lot, this thickness of the wall, because if this thickness will be bigger, larger in magnitude, like if the wall will be more thick, it means that the less amount of heat will be transferred in per unit time. Okay, and in fact, dear students, you know that the rate of heat transfer, which is equals to thermal conductivity, the surface area, and this temperature gradient, delta T over delta X. So you see that this delta X is affecting directly. If this factor is more, then this factor, which is a rate of transfer of heat, will be less. Okay, so we are given the magnitude of all the quantities, and let us see what we need to calculate, and that is estimate the rate at which the thermal energy leaves the room through the wall, giving the answer with appropriate unit. Okay, so estimate, the main thing is estimate the rate at which thermal energy leaves or thermal energy is transferred. So let us solve it. So don't you think that they are asking about to calculate delta Q over delta T? That is rate of heat transfer, right? So we need to calculate this thing. So let's substitute the values. All the values are given. The thermal conductivity is given as 1.3 watt per meter per Kelvin. Okay, that is a unit of this thermal conductivity times area. The surface area is 18 times the change in temperature. Students, is 22 minus 13. That is a change in temperature divided by 0.25. Okay. Now, important thing, the unit should be joule per second, right? Because this is a heat. Okay. And this is a time. So joule per second, which that joule per second is also equivalent to watt. Okay. Because you can also call it power transferred. Okay, so its answer is 842.4 watt. Okay. But when we were solving it, you can see that the minimum number of significant figures is only two in any calculation. Like it have two significant figure, all the numbers have two significant figures. So it is better if we convert our answer into the minimum number of significant figure, which are 2. So 8.4, we will round it off, times 10 raised to power 2 watt. So this is the final answer for this question. So dear students, you see that the one of the unit is this. Let me quickly show you. It will just take less than 1 minute. I have shown you that its unit was joule per second. Okay, how did we get this unit in a fundamental SI unit? So you can write it like this: joule over second, and the joule is equals to newton meter, because that is a unit of work done, divided by second, and the newton is a unit of force, so which is equals to ma. So its unit is kilogram meter per second square times meter over second. So if you solve it, then it will become kilogram meter square second is power negative 3, which is also equals to watt, right? Because if you break down the watt, you will get the same thing. Okay, now let us see what our next question is. So you see that when the heat is transferred from inner side to the outer side, so the temperature will obviously drop, but that temperature drop is not uniform. Okay, uh, because that is due to the heat mechanism, right? So we see that the temperature is dropped like following this negative exponential curve, right? So in this question, we have to outline why the magnitude of gradient of graph decreases. Okay, that's very easy. Like you can draw the tangent line and you can see that the line or the tangent line will become less steep. But let me show you. So our question is, why does the magnitude of the gradient of this graph, right? So first of all, the gradient of this graph, dear students, is delta t over small delta t, right? Means the rate of change of temperature with respect to time. Okay, that is the gradient. But the formula that I have written and that we have used in a previous question was this: ka delta t over delta x, right? So this is a temperature gradient, but with respect to thickness. Now, remember one thing, that the thickness in this heat transfer is not going to change, right? And all the other factors are also constant. So can I proceed it, and can we make our understanding that the rate of transfer of energy is proportional to delta T, right? So if the rate of transfer of heat is decreasing, it means that it is affected due to the change of temperature, right? That's why what we see from the graph, that as the temperature is decreasing, right? Temperature decreasing, due to which the delta Q over delta T is decreasing. Since the rate of transfer of heat delta Q over delta T, and these two are directly proportional, right? Right? These two are directly proportional. That's why if the one is decreasing, the other one is also decreasing, right? That was the the understanding analyzing from from the equation. Now let me show you from the graph, right? So if I keep the interval from 0 to 20, for example, right? So do you notice that during this, what is a change in temperature, right? This is 22 and this is 10, right? So change in temperature is 12 degrees Celsius in the first 20 minutes, right? In the next 20 minutes, you can check that this is a change in temperature, right? which, if I am not mistaken, then it is 3 degrees Celsius, right? In the next 20 minutes, right? And then in the next 20 minutes, dear students, next 20 minutes, the change in temperature is just 1 degree Celsius. So that is overall, you can see that the temperature is decreasing. That's why the gradient is decreasing. Okay, students, so this is a mark scheme which says identify gradient as the rate of thermal energy transfer, and its logic, all of this logic I have explained you with the help of equation and and also from the graph. Okay, now the next question is the pressure and the volume of air in a room remains constant. Okay, so if the pressure and the volume is constant, it means that the PV is also constant, right? That is understood. Okay, now but the number of molecules has increased. How much increased? With what percentage they have increased, we don't know. Determine the percentage increase in the number of molecules of air, right? So let us consider the initially in the beginning, right? At the time t is equal to 0, before any change, right? The number of molecules were n0 and not. So that is n0, for example, and at the after 120 minutes, right now it is n. So what is the percentage increase in the number? So first of all, what with what fraction, right? They have increased. So fraction of increase we can write with delta n, the change in number of molecules divided by the total number of molecules in the beginning, right? So what about the percentage? So percentage increase you have to multiply with just 100%. So first of all, we are making our understanding that what we need to calculate, and then we will use this equation to calculate specifically that thing. Okay, so when we will get this fraction, we will just multiply it with 100% to get the percentage. Okay, so remember this thing basically, that how can we calculate this thing, right? Okay, so let's talk about once again the pressure and the volume. They said that they are same. Okay, so if the pressure and the volume is same, and it means that we want to find the number of molecules, means the fraction of the increase of molecules. So we should use that equation for ideal gas, in which links the pressure volume with number of molecules. Okay, and you know that that one is PV is equals to n kBT, right? It directly links the pressure volume with number of molecules. Okay, so since the pressure and volume is constant, kb is constant. Okay, so can you say that the n is equals to PV over KB into 1 over temperature, right? Basically, that tells us that the number of molecules is inversely proportional to temperature. Because look at this, this is a constant. So we can make a proportionality between the number of molecules and temperature, which are inversely proportional. Okay, so it means that if I say the initial molecule, if I find initial divided by the final number of molecules, it will give us the inverse ratio, because that is inversely proportional to temperature, right? So it will give us the final temperature divided by the initial temperature. Or dear students, you can write here n initial, which we were writing n0, right? And we can write final with just n. Okay, now see that we are getting something out of this equation, right? Don't forget that what we want to find out, we want to find out the delta n over n0, right? Which is the final number of molecules minus initial, because that is a change, right? Divided by, or you can do it vice versa, right? So n0 minus n divided by n0, that's what we want to find out. All right, so the only way is to find out the value of n in terms of n naught, right? Because we don't know what is a specific value of the number of molecules, right? So we will use this equation. What is a final temperature? The final temperature is, if you remember, that was at the time 120 minutes. This is 6 degrees Celsius, which is plus 273 is 279, right? So 279 divided by the initial temperature is, was, if you remember, that was 22. Okay, and 22 plus 273 is 295, right? So I'm going to find its value. You can also write it if you flip it, right? So n over n0 is equals to 295 over 279. So it is 1.057. All right. So from here, finally, we can tell that the number of molecules is equals to 1.057 times n0, right? Very important conclusion. We got the exactly the relation between the number of molecules at the time t is equal to 120 minutes. Now we are going to put the value here, right here. Okay. So finally, so percentage increase is delta n over n0 multiplied by 100% is finally equals to n0 minus n, right? And n is 1.057 n0 divided by n0, right? Multiply by 100%. You can cancel this n naught, yeah, because that is a numerator and denominator. You can cancel it out. And in fact, it will be 0.057 n0 over n0. So that is finally, students, 5.7%. It seems that I have told you the lengthy solution, but actually I have written every step. That's why it seems lengthy, but it's logical flow, right? So I hope you understand. So the last question is describe how the second law of thermodynamics applies to the situation. Okay. Second law of thermodynamics, situation of the room cooling down, right? Now, dear students, here we have to explain the situation according to the entropy, right? The change in entropy, okay? Because the second law of thermodynamics, the one definition of second law of thermodynamics, which says that all the natural systems, all the natural processes flows in such a direction where the net change in entropy, the net change in entropy means that the change in entropy of the system and the change in entropy of the surrounding, the net change of entropy is bigger than zero, is positive. It means that, dear students, that we know that this is a region which is a hot region, right? Okay, you can call it source, right? And this is your surrounding. Okay, so your heat is actually flowing from the hot to the cold with the help of conduction through the walls. Okay, right? So in all the directions the heat is transferred. Now what will happen when the heat will be transferred? Okay, the temperature will drop inside. Okay, so entropy of the room decreases, right? But what about the surrounding? Its entropy increases. So when I say entropy increases, it means that the randomness of the molecules in the surrounding increases. And secondly, it means that now whenever entropy increases, it means that now there is a more less availability, right? There is a now less availability of the useful energy. So the heat that is lost to the surrounding, it cannot be retraced, it cannot be retrieved. Now that is gone into sink, that is gone into surrounding. You cannot utilize it. Okay, so that is why I'm saying it is unavailable amount of energy, right? That you cannot retrieve. So it means that the entropy increases. Okay, so second law of thermodynamics says that the net change of entropy for any natural system, if it is not reversible, right, is always bigger than zero. It means that the change in entropy of the system, which although you know is negative because it has decreased, plus the entropy of the surrounding, which you know that it have increased, even if you add these two, it will still be zero, bigger than zero. It means that I'm saying the net is positive. So what Marx scheme says that heat is removed from the room, so entropy decreases. Obviously, we discuss about it. So the same heat is deposited at a lower temperature, which means the surrounding, which we can also call sink. So outside entropy increases, right? But what is a net change? The entropy change of universe always increases, which I have shown you with the help of this thing, right? I hope you understand this whole solution. All right, so let me know in the comments.